what I'll do is try to recreate on this board, this lovely board that now I conditioned it. I've got the markers that go with it. So we had two scenarios, and we're talking about spontaneity, and it's all about dispersion, right? So we want to disperse energy and we want to disperse matter. So if you disperse energy out, you guys told me that that's exothermic, and we said that the delta H is negative, right? Okay, and if you take your matter and you disperse your matter out, that means that it's making more chaotic, so your entropy is increasing, right? So your delta S there is greater than 0, right? Yeah. And this actually is spontaneous. And we talked about some different scenarios, like, well, what if one's out and one's in? Well, it kind of depends. We'll be talking more about that coming up. And then we have this, so that's what the universe wants to do. Then we have this scenario where it's going in. So energy in, that's endothermic, and your delta H is positive. And matter in, things are becoming more ordered, which goes against what the universe wants. That's why my house is a mess. So matter in means that your delta S will be negative. Okay? So we're going to kind of pick up where we left off. So Gibbs free energy actually looks at your enthalpy, your H, and your entropy, your S. And don't blame me that they both sound so similar to each other. It can't be just me that it bothers. So Gibbs free energy of a reaction, blue box alert. So this blue box information then will be on your sheet that you'll have for your Unit 5 exam. So we can test what a reaction is going to be with regard to spontaneity by coming up with a value for delta G. Delta G is delta H, enthalpy, minus the temperature at which it occurs, times delta S. And the way this works is, I might go ahead and just put this up here, just because I'm having fun writing on this whiteboard. And it actually wipes off too. So delta G, Gibbs free energy, is equal to the change in, if it's at standard conditions, and we'll put that little knot there, minus T delta S. And it says if it's negative, if this thing is negative, then it's spontaneous. And I know we had like a happy face over here and a sad face over here. Okay. Now the slight difference, I had to go back and forth. What's the difference between those two slides? Right. One's at standard conditions and one's at any conditions. Okay. It's like, really? I like the same slide. The first one was standard? Yeah, if it has the knot, that's standard conditions. 25 degrees Celsius and 1 bar pressure. And 1 molar for aqueous solutions. All right. So here we go. If the change in Gibbs free energy of the reaction is negative, less than 0, it's spontaneous as written. If your change in Gibbs free energy that you calculated is 0, okay, the system isn't going left to right and it's not going right to left. It's like stalemate. It's at equilibrium. If you have a positive Gibbs free energy, change in Gibbs free energy, then that means it's non-spontaneous. And then all you got to do is swing it around the reaction arrow to make it spontaneous. I just think that's so funny. Non-spontaneous is written. That means, in other words, it will go from right back to left. This actually, I'm pretty sure in my notes, this change here should say system. I'm not sure why it says change. It doesn't make sense to me when I was reading it. One of the things we've been talking about is that, you know, if this is our system, what's outside our system? Surroundings, very good. And where's the universe? All of the above, yeah. The change in entropy of our system is equal to Q is equal to mc sub p delta T. Q is the change in thermal energy. Change in thermal energy over time, and if it's happening at constant pressures, then it's also the change in enthalpy over time. I'm sorry, over temperature. Change in thermal energy over temperature, change in enthalpy over temperature. It means the same thing. All right, so here we go. At equilibrium, delta G, change in Gibbs free energy is equal to 0. And in that case, we actually can rearrange that top equation to look like this. The temperature times the change in entropy is equal to the change in enthalpy of the system. We can rearrange at equilibrium then. The change in entropy of the system is equal to the change in enthalpy of the system divided by the absolute temperature. These capital T's are absolute temperature, which we've just kind of come full circle. That's what I said a minute ago. At equilibrium, stalemate. Okay, I gotta keep going. She didn't have her notebook, so she's taking notes as she goes. But we're gonna keep rolling. Okay, so we're after negative delta G to make it spontaneous. Let's look at some situations here. Well, what if we have negative delta H, energy out, favors spontaneity, and what if we have a positive delta S? Now, a positive delta S, what will that do? Well, if I plug that into this term up here, guess what? If this is positive, then that makes this negative. And that's what that's saying. I hope that makes sense. Because in that equation up there, it's the quantity of the change in enthalpy minus the absolute temperature times the change in entropy. So actually, this is what we're describing here, aren't we? S is positive. So actually, it's exothermic dispersing energy. It's increasing disorder, dispersing matter. And by golly, you can't do anything with those numbers to get anything other than a negative delta G. It just is. This is negative, this quantity is negative, and so it's always going to be spontaneous. Now there's three more scenarios. What about this one? Delta H is negative, okay? So it's dispersing energy, but in this case, our delta S is negative. So we've actually got a mixed sort of thing where this guy right here favors spontaneity. I'll just put favors, and I'll just put the word disfavors here. It's a mixed bag, and it kind of depends. So it's exothermic dispersing energy, but it actually has matter coming together because your entropy is decreasing. So it might be spontaneous, okay? So it could be. We could get a negative delta G, but in that case, the thing that favors is going to have to actually be larger than the thing that disfavors. Does that make sense? This term that favors is going to have to take over. And if that's the case, we say it's spontaneous, but it's enthalpy driven. Okay. Now it might be, you know, I'll put an if here because it may not be less than 0. Okay. So notice that the conditions that would favor your delta H to take over is if your T is small. You know, you want this guy, you want the absolute value of this quantity to be kind of small. Well, the smaller your temperature is, the more likely that is to be the case. All right, that was 2 of 3 scenarios. Let's look at this one. Oh, in this case, we have a positive delta H, which you would tell me that's endothermic. So we have a positive delta H, so that's the opposite. That's not going to favor spontaneity. And we also have a positive delta S, which does favor spontaneity. So I'm going to put disfavor over here, and I'm going to put favor over here. It's all about dispersion. So endothermic, because of our positive delta H, so energy coming in, it is creating disorder, and that's favored, dispersion of matter. So it's positive if it's possible to make it spontaneous. If it's spontaneous, our delta G is 0, and that can only be the case if this second term down here, the one that favored it, is taking over. Okay, if that term is taking over, and this one that disfavored spontaneity is minimized. So in that case, we say that it's entropy driven. Okay. And what do you think? High or low temperatures would favor this then? High temperatures, yep. So just mathematically, whether you're thinking, you don't have to I wouldn't necessarily think through it. I look, well, if I want this to take over, the higher my T is, the more that this product is going to be higher than my delta H. Exactly. So that's 3 scenarios. The last one actually is this one. So in this case, we have it is endothermic, a positive delta H, and our delta S is negative. So actually, it's becoming more ordered. A matter is coming together instead of being dispersed. So in that case, good point. So it's endothermic, and it's creating order. It's going against the grain, against the laws of the universe. So your delta G, your Gibbs free energy, will never be negative. Not to say that we can't make this happen, it just means that it won't happen spontaneously. So this reaction will never be spontaneous. Makes you want to go out and find an exception, doesn't it? So I like this table from OpenStax, I think. It talks about, you're going to see the 4 different scenarios. Endothermic, exothermic, let's see, let's put endothermic would be, let's just put the one that favors. So exothermic favors spontaneity, right? An increase in entropy favors spontaneity. So over here, and this is the first scenario we looked at, it's all green and all that. So your Gibbs free energy is always going to be negative because your delta H is negative and your delta S, which was positive by the time you get it times negative T, it's negative. Here we got a couple of different options here. These actually, notice in the first one, we have something, the entropy favors it and the enthalpy disfavors it. So it kind of depends. We said at high temperatures, this could happen. Down here in the lower right-hand corner, this could go if your enthalpy term takes off, and this will happen at low temperatures. And then what's this last one? No, it's not happening at all. Yep. Quite cool. We got the whole color coding red. Okay. If you are taking in energy, endothermic, and you're also making something more ordered, putting matter together, it's not going to be spontaneous. Okay, this one confuses me a little bit, but it's trying to show the same thing. I see along the x-axis, we have increasing temperatures. So this is actually trying to kind of show you, and it's color-coded just like we looked at. So here we see green, going to happen regardless of temperature. Red, not going to happen regardless of temperature. I guess it makes sense when you take the context of the previous video. And then these crisscrossing, we said that if your, if your your delta H term is what's going to hopefully make it spontaneous. It's going to happen at lower temperatures. Okay, I guess I buy that. And over here, if it's your delta S term that's going to make it spontaneous, it's going to happen at higher temperatures. So it's just a little bit like, really? So it's just trying to kind of summarize the information. So Gibbs free energy. Those, and we're going to see them again, kind of excerpts from the appendix of your textbook, where they had thermodynamic quantities, and there was a column for delta G, right? So actually, you can do the whole product, summation of the products. It's always final minus initial. So summation of the products minus summation of the reactants to get to your delta G. Or you can use this up here. So either one, you can get your delta G. So I think we're going to work a couple problems now. Just a little bit about Gibbs free energy. Now, this little f means of formation. So it's a subtle thing. It's a subscript, not a superscript. And we ran into an f before when we did I think we did the standard molar enthalpies of formation. I don't know if you remember, we did the delta H naught sub F. I think we talked about those before. Same thing, of formation. So, Gibbs free energy, formation of 1 mole of compound from its elements in their standard states, their standard conditions. By definition, the delta G, the Gibbs free energy of formation of an element, is 0. Of an element in its standard state at standard conditions. Have to be a little bit careful because remember standard conditions, and you have to use your common sense. Standard conditions, you're talking about 25 degrees Celsius, and I'm pretty sure it's 1 bar, which is 1 bar, which is close to one atmosphere. So, for instance, iron, Fe, solid, right? So the Gibbs free energy of formation of iron is 0 in its solid state. Iron liquid, it's actually not going to be 0. Okay. So yeah, so we see H2, O2, N2. The standard state of that element under standard conditions. Okay, well, it's diatomic. Standard state of carbon is the allotrope graphite. Okay, the allotrope carbon, not its standard state. This is where this is different than these Gibbs free energy of formation are different than our entropy, our S's. Our S's always have to be positive, right? Because everything has an entropy, a bit of entropy to it, unless it's in its crystalline state at absolute 0. Or these actually, you can get positive and negatives. So that's kind of fun. So again, these are kind of the same tables we looked at before. We were looking at entropy before, and now we're looking at delta G. And that would be, I'm pretty sure that, I'll have to double check, but I'm pretty sure that these actually are, these are of the formation. These are the delta G's, Gibbs free energy of formations, just as I believe that these delta H's are of formation, enthalpies of formation. Not sure what that 1 is. Okay, let's work a problem, shall we? So the combustion of methane. Actually, there's a homework problem that you had to do for today. We talked about the combustion of propane. So combustion is combining something with oxygen. Here's the balanced equation for burning methane. Okay. So we can come up with some quantities here. We can come up with the change in enthalpy, entropy. Okay, we can come up with the change in entropy, and once we have those two quantities, I'm pretty sure this is how we're going to work it, we can come up with the change in Gibbs free energy. Once we come up with the change in enthalpy, if it's positive or negative, we'll be able to know if it's endothermic or exothermic. Once we come up with the change in entropy, if it's positive or negative, we'll know if it's increasing entropy or decreasing entropy, becoming more disordered or ordered. And then if we come up with the delta G, we'll be able to know if it's spontaneous or non-spontaneous, just if it's negative or positive. Okay, so this is just to kind of remind you, reach overhead. Delta H positive means endothermic, negative means exothermic. Delta S positive means more disorder, negative means more order. Delta G positive means non-spontaneous, negative means spontaneous. And again, we kind of have a little crisscross thing going here. Because to me, if you're trying to if you're trying to make your reaction spontaneous, those are the two dispersions of energy. All right, so here we go. These are just excerpted from those tables. So if you would look up, see, yeah, now I actually have formation. If you were to look up the thermodynamic values for the two reactants, methane and oxygen, this is what you have across the board. The products, carbon dioxide and water. The hardest thing in working this sort of problem, whether it's homework or on the test, is staying organized and applying this equation. So what I like to do is, although I didn't do it on my answer key for the homework that's due today a little bit, but I like to work on the product side and then work on the reactant side. I think I didn't do it on my homework because it just wasn't complicated. If you have more than two or more reactants or products, it does. So looking at the product side, we need to come up with the carbon dioxide in the water. Stoichiometry enters in. Stoichiometric coefficient in front of the CO2 is 1. So that's where the 1 mole of CO2 comes from. From the table, we look up the enthalpy of formation, and we get a negative 393.5. The units at the top of the column were kilojoules per mole. And then the other product is water. The stoichiometric coefficient in front of water is 2. So we'll have 2 moles of O2 times, from the table, negative 285.8 kilojoules per mole of H2O. And then you do the magic, put it in your calculator, and this is with regard to rounding. These numbers, the stoichiometric coefficients 1 and 2 are exact. So actually, it's kind of like, bottom line is you can keep 1 decimal. So we end up with a negative 965.1 kilojoules of energy. So that's the product side. And I start a new line. The reactant side looks like this. We had the stoichiometric coefficient in front of the methane was 1, so 1 mole of CH4. From the table, you're looking at negative 74.8. Forget that extra little, I don't know if it's 0.80 or it's 0.8, but anyway. 74.8 kilojoules per mole. The other reactant was oxygen, so 2 moles of O2. Oh yeah, remember that when we talked about standard molar enthalpies of formation, not just even the Gibbs free energy of formation, but also the enthalpy of formation is 0 for elements that are in your standard state. Standard conditions. What's that?
Oh, it's okay. I'm sorry. I was reading it wrong. I thought it would be like the other side of the formula, the CO2 and the 2H2O.
Yeah. So I can almost do the math there. So you end up with negative 74.8 kilojoules of energy. So we're ready to go ahead and do one last subtraction. We're going to take that number we got in the front part and subtract the number we got in the next part. A very common mistake in this sort of problem is to lose your negative sign. So we have negative 965.1 kilojoules minus a negative 74.8 kilojoules, which the minus and negative is like a plus, right? Which gives you negative 890.3 kilojoules of energy. So that's your delta H. Endo or XO? XO. Favors, disfavors? Yep, favors. So put a smiley face there. The universe is happy. So let's, so since it's negative, since delta H is negative, less than 0, then it's an exothermic reaction. Let's check out the delta S. And again, we're going to go back to that table a few pages ago. Focusing on the product side, we had 1 mole of CO2 formed. The delta S in that column for CO2 is 213.7. The units then are joules, not kilojoules. The units are joules per mole Kelvin. So the units of entropy are different than enthalpy. And, you know, working a problem on a test or whatever, you'll be given that information if it's in the column or if it's in the so. Then we're also produced 2 moles of H2O. And we can see that the entropy for H2O is 69.9 joules per mole Kelvin. We go ahead and knock that out. That leaves us with 353.5 joules per Kelvin. And then the reactant side, we had that 1 mole of methane, 1 mole of CH4, times 186.3 joules per mole Kelvin. And then we had the 2 moles of O2, which actually with regard to entropy has an entropy of 205.1 joules per mole Kelvin. Pop that into our calculators, give ourselves 1 decimal. And you should come up with 596.5. And then again, units now would be joules per Kelvin. And then ready to do one last subtraction. So we're going to take our 353.5 minus 596.5. And we're going to end up with a negative 243.0, and then units would be joules per Kelvin. So is this becoming more ordered or disordered? More ordered. Does it favor or disfavor? Yep. Disfavor spontaneity. So, joop, 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 joop. Yep, since it's negative, it's creating order. So we could actually go back to our, we could do a similar thing for coming up with our delta G, but let's do it this way instead. So the values you had earlier of this, you have your delta H, you have your delta S, so let's plug them in. So now then your delta G, your temperature. Now sometimes the temperature is a little elusive, but this hopefully I'll scream at you, but if you're working with standard conditions, you know that that's 25, and it's thermodynamic, standard thermodynamic conditions, it's different for gases. But you know that it's 25 degrees Celsius. So we need, this has to be Kelvin though. You have to be Kelvin temperatures, Kelvin units. So we have to add 273.15 to get, and I'm not sure why. This, to me, the standard conditions are like, right, it's exact. So to me, I think you could almost do 25.00 plus 273.15 and get 298.15, but that's okay. That works. All right, ready to plug. So delta G is negative 890.3 kilojoules. That's our delta H. Minus 25 degrees Celsius, or 298.2 Kelvin. Now, our delta S, notice we have to fix it. We have to do a little bit of fixing, because this was our delta S, but I need to add, I need to mix apples with apples. So I'm taking my delta S, which is negative 243.0 joules per Kelvin, and I'm converting it to converting it to kilojoules by that last term. 1 kilojoule over 1,000 joules. And then, drum roll, you get negative 817.9, and units would be now kilojoules. So how many people think this is exothermic? Or how many people think this is favored? How many people think it's disfavored? I mean, how many people think it's spontaneous? That was the word I was after, spontaneous. How many people think spontaneous? How many people think it's non-spontaneous? Yep, it's spontaneous. Yep, because it's negative. So less than 0 is spontaneous. So, yay! It's spontaneous, and actually what drove it? The delta H drove it. Yep. So it's enthalpy driven. Yep. Spontaneous, enthalpy driven. I can't remember if I have a slide saying that, but it is. All right. Spontaneous. Right, enthalpy driven. All right, one more problem, hopefully. This one's like, really? Is that a real problem? Okay. We basically have the same material going from a solid to a solution, which is cool. What do you think? Is enthalpy or entropy increasing or decreasing? How many people think the entropy is increasing? How many think the entropy is decreasing? It's increasing. Yep, entropy is increasing. So let's come up with some quantities. And actually, in the back of your OpenStax books, there is ammonium nitrate solid and ammonium nitrate aqueous. So the values are there. So we're going to knock out these 3 quantities again. And based upon the sign of the enthalpy, we'll know if it's NO or XO. Based upon the sign of the delta S, we'll know if it's, but you already told me it's becoming more disordered, so we should expect what? A positive delta S, right? And then what the delta G is to know whether it's spontaneous or non-spontaneous as written. So yep, these are actually in your OpenStax books. And those will be the quantities we'll be using. This is one where, and I said on your homework, I didn't do the whole, this is a little bit sloppy to me. So what are the stoichiometric coefficients of the equation on the previous slide? 1. Okay, so since they're just 1 mole, all I did was I grabbed, this is my product, let's see, products. This is my product. And this is my reactant. So it's always products minus reactants. So that's why you see this number, negative 339.9 minus this number. Okay? Delta S, similar. It's products minus reactant. So products minus reactant. And again, the only reason I can do this is because the stoichiometric coefficients are 1. And then last but not least, you guys have this written down? Okay. Last but not least, oh, can't see through it? No. So why do you think for delta G I just went, I'm like, oh, they're already on the table? I guess it's a rhetorical question. This was easier to do than to use this one over here, but I could have. I sure could have. You should get the same answer. All right. So the enthalpy, delta H. So is it endo or exothermic? Endothermic, yep. Does it favor or disfavor spontaneity? Disfavor, perfect. Okay, what about the delta S? Is it more ordered or disordered? Disordered. Okay, does that favor or disfavor spontaneity? Favors, perfect. What about the change in Gibbs free energy? Is it spontaneous or non-spontaneous? Spontaneous. Awesome. Well, since we kind of have one favoring and one disfavoring, what's the driver? Yep, spontaneous, and it's entropy driven. Exactly. Entropy driven. Here you are.
Yeah, the second one down, disorder.
Becoming more disordered, and that favors spontaneity.
Okay.
Yeah. Very good. So it's all what you said. You said it was endothermic since it's a positive delta H. You said it was becoming more disordered since it's also a positive delta S. And since it ended up being a negative delta G, it's spontaneous. And it's driven by the entropies. Cool. So this is kind of a subtle thing. We can take this, and this is at not equilibrium. We can use this relationship to come up with a temperature, a tipping point at which it will be spontaneous. So let's go back and look at the situation where it's at equilibrium. It's not going from left to right. It's not going from right to left. Okay, it's at equilibrium. The rate in the forward direction is equal to the rate in the reverse direction. So delta G is going to be equal to 0 at that point. Remember, this is the convention we talked about with regard to Gibbs free energy, changing Gibbs free energy. When it's negative, it's spontaneous. When it's equal to 0, it's at equilibrium. If it's positive, that means that it's non-spontaneous as written. Oh yeah, now I forgot what it is. So we have some kind of interesting kind of compare and contrast with regard to equilibrium. Seeming like eons ago, in Unit 2, we talked about chemical equilibria in general. No, that's in Unit 3. Unit 3 were equilibria. Unit 2 was rates, reaction rates, mechanisms. So, but anyway, remember that Q is the snapshot. Okay, when Q is, or QC is equal to your equilibrium constant, then it's at equilibrium, is that? We kind of have a similar situation where when delta G is equal to 0, it's also at equilibrium. And here in a minute, I'm going to actually link delta G and Q. Well, we said that when Q is too big, when your snapshot's too big compared to your equilibrium constant, we said, oh, sorry, too small. When Q is too small, that's what the lesson means. When it's too small, that means that you need more products because products are on the top, okay? So some of your reactants are going to go to form products. Well, similarly, when we said when Gibbs free energy is small, when it's, or less than 0, specifically, not just small, just less than 0, we said it's going to be spontaneous as written. And again, that's reactants going to form products. One more last kind of compare and contrast. If your Q, your snapshot, is too big, that means that you have too much product and it's going to have to go back to form reactants. So similarly, if your Gibbs free energy is greater than 0, then also it's not spontaneous as written, but if you, by golly, you want to get it spontaneous, you just swing it around the reaction arrow. So we kind of have these kind of compare and contrast things going on. As it turns out, there's a definite relationship between Gibbs free energy, the snapshot, which is Q, and the equilibrium constant K. This is not in a blue box, so this won't appear on your sheet for working, but this is in a blue box, so it will appear on your sheet. So the relationship between Gibbs free energy and the equilibrium constant K is this. Gibbs free energy of a reaction is equal to negative R, the temperature at which the reaction is occurring, times the natural log of the equilibrium constant K. Okay, so let's look at that blue box equation and apply it. So we're supposed to come up with an equilibrium constant K for this reaction. Now, already you might be like, an equilibrium constant. Well, I always thought when methane burns, it's a one-way thing. It's not going back and forth. Okay? You're like, really? Equilibrium? Well, if something is really favored, and actually we're going to see that here in a minute, if it's really favored in the forward direction, is the K high or low? Is the K big or small? Products over reactants, so it's big. Yeah, the K is really big if it favors the products. So let's see what we can do with this. Previously, we came up with the Gibbs free energy for this reaction, negative 817.9 kilojoules. So we're going for K in this relationship. So to get K in this relationship, we're going to have to do some funky things. To get K from ln of K, what we can do is recognize that if you take, how's this work? If you take E raised to the ln of K, you get K. E raised to the ln of K, you get K. And we're going to make use of that. So if we rearrange this, you get the ln of K is equal to negative delta G over RT. And like I said, if you take both sides, E raised to that quantity, looks like I'm going to do it. I'm going to kind of do it in stages. So here I've got the ln of K is equal to negative 817.9 kilojoules per mole over R 0.00831 kilojoules per mole Kelvin. And then also in the denominator, 298 Kelvin. And hopefully we're all okay that that 298 came from 25 degrees Celsius. Whew. Notice the units that cancel. So we have Kelvin I love canceling units. Kelvin cancel here, kilojoules per mole cancel here. So we got a unitless number here, which is perfect. So you're going to get 330 with 3 sig figs. Now here's where I'm going to do my little magic up here. So to get to K, all we got to do is take E raised to the 330 power. This is a very big number. Check out that number. Woo! That is one big K. E raised to the 330th is 2.08 times 10 to the 143rd. I don't think we've had a number like that yet. Okay then. So I didn't leave you much time, but please take the survey, because that's it. That's all I got. All right. And it's open today and tomorrow, and that's it.
Okay.
So take it for all of your classes.
Can I ask you a question?
Uh-huh.
Okay, like can you go back a slide if you don't mind?
This one?
Yeah,
Okay.
me and this dang calculator stuff. Okay, now, I'm not using that, yeah, I'm using that.
Oh, you're gonna use the round one. So you're gonna do shift.
That one, 330.
Yep, that should do it.
Oh, shoot. Okay, there.
Right. Oh, wait.
Oh, I did the wrong one. Okay, there. 330, there. Enter.
I don't know, your calculator's not
Because
working
it
right.
did it before and it came up just with a different number. That's all. It was only like 10 to 14 or something. It wasn't 143. Maybe I couldn't read it
I
right.
don't know if it's in a different mode,
But
but you're doing it
There's
right.
one other question I got, and I feel really stupid. I don't know if I'm having a brain fart or what. But when you were showing us the CH4, and the only, oh wait, no, what was the one that was just a liquid?